Chers professeurs, chers étudiants, bonjour. Aujourd'hui, c'est la 5e conférence dans la série des conférences intitulée « Les discussions mathématiques franco-marocaines » organisée par le Laboratoire de recherche analyse numérique et analyse non linéaire de la Faculté des sciences de Tétouan, Université Mohammed et le Laboratoire Analyse, Géométrie et Application de l'Université Sorbonne Paris Nord en coordination avec mon cher collègue, le professeur Benoît Rito. Dorénavant, les discussions mathématiques franco-marocaines seront modérées par moi-même et par le professeur Benoît Rito. Je tiens aussi à remercier mes collègues du laboratoire LAGA et LAGA pour leur suivi et leur soutien aux discussions mathématiques franco-marocaines. Les 4 conférences du professeur Hatim Seaid, du professeur Frédéric Bourdeau, du professeur Olivier Lafitte, du professeur Benoît Rito sont enregistrées et disponibles sur la chaîne YouTube LAGA-UAE. La conférence d'aujourd'hui sera animée par le professeur Seaid Mohammed de l'Université Durham de l'Angleterre sous le thème « Les éléments finis enrichis où en sont les mathématiques ». Avant de présenter la biographie de notre conférencier Seaid Mohammed, je passe la parole au professeur Benoît Rito pour dire un mot sur la conférence d'aujourd'hui.
Bonjour, merci Arish, bonjour à tous, ravi de vous retrouver pour cette cinquième conférence. Donc, je rappelle rapidement comment fonctionnent nos discussions. Donc, elle dure environ, on aura un exposé d'1 heure suivi d'une discussion d'environ une demi-heure. Et vous êtes invités à poser vos questions sur le chat qui est sur le côté dans Google Meet. Et les questions ensuite seront posées, vous pouvez éventuellement garder vos questions pour la fin, mais pour s'en souvenir, ça peut être une bonne chose que de les écrire sur le chat durant la demi-heure de discussion. Nous serons limités à 1h30 en tout, parce que c'est la durée maximale d'enregistrement pour pouvoir mettre en ligne l'enregistrement de l'exposé. Voilà. Et donc, nous recevons aujourd'hui Mohammed Seaid, qui est de l'Université Durham, en Angleterre, et qui va nous parler des éléments finis et de faire le point sur cette partie des mathématiques qui est importante, qui a une longue histoire déjà, qui remonte au moins à Euler, et les éléments finis enrichis. J'avoue ne pas être spécialiste de la question, donc je ne sais pas ce qu'on va apprendre, mais on va sûrement apprendre beaucoup de choses sur des mathématiques concrètes, des mathématiques qui s'appliquent, et avec ce double défi qui est un petit peu la marque de nos discussions, de l'intérêt théorique d'une part et de l'utilité pratique d'autre part, pour apprendre les mathématiques qui est utile aux doctorants, leur permettre de s'ouvrir l'esprit avec des mathématiques variées. Voilà. Merci.
Merci, professeur Benoît Rito. Maintenant, je vais présenter une courte biographie de notre conférencier. Le professeur Mohammed Seaid est d'abord diplômé de l'Université Mohammed de Tétouan avec une licence en mathématiques appliquées. Il est allé en 1994 à l'Université Complutense de Madrid, en Espagne, pour faire les études de doctorat. En 2000, il est allé à Darmstadt Technische Universität et à Kaiserslautern Technische Universität en Allemagne, en tant que post-doctoral, chercheur associé et professeur assistant. Depuis 2017, il occupe un poste de professeur à l'Université Polytechnique Mohammed VI de Bengri. Il occupe également un poste de professeur à la School of Engineering and Computing Sciences de l'Université de Durham au Royaume-Uni, où il a vécu à partir de 2007. Depuis 2019, il occupe un poste de professeur invité à l'Université d'aéronautique et d'astronautique de Nanjing en Chine. Le professeur Seaid est responsable du groupe méthode numérique du groupe PDE et vice-président de la Société marocaine des mathématiques appliquées. Ses travaux de recherche se sont concentrés sur 2 domaines. Premièrement, la modélisation des écoulements d'eau de surface libre et du transport des sédiments. Et deuxièmement, le développement de méthodes numériques robuste pour la mécanique du calcul. Une grande partie de ces travaux a été menée sur des plateformes de calcul haute performance, en collaboration avec des collègues de Fraunhofer Institut Techno and Mathématiques, c'est en allemand ceci. En Allemagne, il a développé des méthodes Boltzmann-Andreas pour les équations des eaux peu profondes dans les courants de marée. Les travaux théoriques et informatiques se sont récemment concentrés sur l'application des méthodes de Boltzmann-Andreas pour les problèmes de déformation, qui fournissent un cadre de calcul pour examiner les performances des méthodes de Boltzmann-Andreas dans des domaines spatiaux avec des frontières mobiles. Depuis qu'il a pris son poste actuel à Durham, il a effectué des recherches sur l'utilisation et le développement de méthodes adaptives de volume fini, appliquées en particulier aux problèmes de génie hydraulique. Il a étudié des discrétisations bien équilibrées pour des équations en eau peu profondes sur une topographie non plane en utilisant des techniques de volume fini. Le professeur Mohammed Seaid a publié plus de 150 articles dans des revues internationales sur la dynamique des fluides computationnels et les méthodes numériques pour les interactions entre les sédiments et l'eau. Il est membre du comité de rédaction de 6 revues, a organisé de nombreuses conférences et 4 écoles de printemps sur les méthodes numériques pour les EDP. Franchement, nous sommes fiers de vous, professeur Seaid Mohammed. À vous la parole.
Merci beaucoup, professeur Arij et professeur Benoît Ritou. C'est un grand plaisir pour moi pour ce séminaire et pour l'invitation. Merci beaucoup. Et vous me permettez de parler en anglais. Peut-être c'est très confortable pour moi et à l'aise. Mais s'il y a des questions et des remarques à la fin de la présentation, vous pouvez poser des questions en français ou en arabe. Mais pour moi, c'est peut-être c'est mieux de présenter en anglais et après on passe à des questions en français. Okay. So as I said, it's a pleasure for me to talk today in these discussions of mathematics between France and Morocco, which is an honor for me. And it's a pleasure because I am back in my home university where I studied applied mathematics before moving abroad. And also I'm pleased to meet friends and colleagues in this seminar, and hopefully it will be very useful for you. So when I have been approached by Professor Arij to talk about something within these seminars, I was hesitating which topic I should talk. So, and because the diversity of people attending this lecture maybe would be very difficult to find a common background to give a talk where people can follow you. So what I have prepared in these slides, so something I have been doing there in the past few years, and I try to make it as simple as possible, at least all the people can understand what I'm talking about. And I will talk about some enriched finite element method, so where I think this field of research now is crying for analysis and mathematical theory of foundations. So I'm not going to teach you finite element methods. This is something you already know. So this finite element method, which has been developed a long time ago, has been used by engineering to solve many problems. As you see in this slide, these figures are not mine, as I said, so this is something I collected from a book. And you can find these applications in many areas. So finite element methods have been used for submarines, like you see here. So in oceans or circulations. And then they have been used widely in design and aeronautics. So many design we do for planes, they are based on analysis or finite element analysis. So recently, finite element analysis has been used also for COVID-19. So they use it for simulating what happened or the impact of these viruses on the lung. It has been also used in bioengineering. If you see, this is the hearts. They try to understand the contractions or the stress distribution and the mechanical behavior of the hearts. And they have been also used frequently in the automobile and also in the car design, like you see here, there's a turbine, and also in the engine of many car industry. So that's something we already know. Maybe finite element is well established, has been designed, and also there is many commercial softwares you can use to run your code. But this work, and it has been developed for years, not by mathematicians. So, and this is why I put this picture of these nice people which contributes to finite element theory. And the starting was on, I think, Galerkin, which maybe people working on finite element analysis, they know Galerkin or method has been widely used for finite element analysis. And there where Galerkin was trying to do when he did, well, that time wasn't known as a finite element analysis, but widely used by stress analysis or structural analysis. So Galerkin tried to estimate or to calculate the stresses on a bridge, which is a civil engineering stuff. And instead of doing the whole analysis in a bridge, he was saying, if I discretize the bridge into small elements and try to understand if I apply the load in a simple element, can I describe the bridge into a few elements? That was his concept. And later on, he will develop a nice theory. So Galerkin is a Russian, and he did structural mechanics and also some applied mathematics later. And the best paper he wrote, he wrote it on while he was in prison, because he fled the Nazis, and he was doing some nice work at the prison. So later comes the Walter Ritz, and also this projection of Ritz. If you know about the finite element, Ritz is a Swiss, also he did most of his work on engineering, and he developed the projection, and he did some work on before the finite element concept or literature coming into business. Then Richard Current also, well, he's a German, and he wrote a very nice paper or book, What is Mathematics? And this very good book when he developed some of the stuff we are using in finite element as well. But the one who developed the concept of finite element analysis and finite element method is the Hrenikov. And Hrenikov, he wrote the first paper and also about the finite element, and it's used for structural analysis. All these papers, as I said, are engineering. And later comes the Greek or the Argyris, which I think he mostly creates the finite element background while he was in Stuttgart before moving to ETH University in Zurich. So he did a lot of work there for finite element analysis. Later it comes Clough, and Clough is the one who I think did most of the mathematic or background of foundations for the finite element analysis, and he brought all these engineering concepts and tried to put them into mathematical languages. And he wrote many papers, and one of the paper who was very cited in this area. Zingievich, and that's where I think the creator of the mathematical basics for finite element analysis. Again, Zinkiewicz is a structural mechanic. So he was in Swansea. I met him in 2004. So, and he developed a lot of work into the finite element analysis, and he was organizing every year a conference on finite element analysis. However, all what I said up to now, that was engineering background. So that people, they use finite element to do many work in solving problems. But Babushka was, I think, the one who developed a lot of theorems, error estimate, and also some stability, P convergence, H convergence for finite element analysis. And maybe most of the work or papers on mathematics or theory is because or maybe contributed or attributed to Ivo Babushka. Ivo Babushka was born in Prague, and then he decided to move to US, and then he developed some codes with some industrial finite element developer. And he was retired recently. I think it's 2018 when he retired after 92 years working on the academia. Okay, so to please some people, I put here something. I know people, they won't understand this, but I know some guys, and one who is attending the seminar today, he's very proud to, and he was doing some work or some search here. So this guy is Ibn al-Banna al-Marakushi. He's a Moroccan scientist and scholar. So he was living on the 13th centuries, and he developed some nice and good stuff on math. And he wrote, I think, 58 papers or books. And one of the books, so is Kitab Raf' al-Hijab and Wujub A'mal al-Hisab. So this is just to reveal I think the veil on works on the scientific computing. So in this book, they found something. He was trying to explain fractions, and he's good in fractions. This is a very known theory he developed on that, but he was trying, he talked about, in this book, he talked about something we call in Arabic tajzi' al-mujazza. I discretize the discretized, or discretization of the discretized. And that's something is people, they trying to link this to finite element analysis, which I doubted. I don't believe in conspiracy theory, and but to please these people, yeah, maybe if we look back to the history, we might find something connected to finite element analysis. Go back to these Wuld al-Banai, like we said. So this is a son of the builder, and he did a very good work on mathematics at that time. Okay, so but if I give you a summary on a brief summary on finite element analysis, and as I said, so from 41 to 7 until 70 or 65, all that area was dominated by engineering. It's no mathematics at all there. So I think the finite element analysis started from the 41. It wasn't called finite element, it was called matrix, and sometimes called structure in engineering, and was called later stress analysis, and until I think 72, or then the word finite element come into business. 41, I think Hrinikov and the current developed discretization of the methods to calculate the stress, and that's elasticity mainly. So they take a bridge, they load it, and they say what would be the stress on this bridge. And also if you have a building and then you have a wind blowing on that building, so we want to estimate what kind of the stresses and the failure for that building. So this is what the engineer, they did. 56, I think Clough, when he published the first paper, wasn't finite element really at that time. It's called also finite element for structural engineering or structural building. So that was the first article or paper. So in 59, General Motors and IBM companies come into business, and then they develop the first computer, I think, and they call it designed augmented computers, and that was usually used for car design and also for small beams. Later in 60, I think Fitter, who worked for Boeing, they started to do also some codes, and they use it for designing the cockpits for the pilots and also for aeroplane. 65, when Nastran comes into business again, so this is NASA structural analysis. They develop some nice finite element, and then they put it into work to design mainly for their work on the aeronautics. So in 67, where Zingievich published the first paper, and then I think the first paper which still referred to as a Bible for the finite element analysis. And then on 72, there where Babushka, I think he started to do analysis on finite element, try to prove some convergence and the stability for the finite element methods. In 79, there where Babushka was very active, very young researcher, and he did a lot of analysis. And then he contacted Zappo, and Zappo, he was in the industry, was engineering, it's nothing to do with math. But Babushka, he took his work, and then he wrote him once. He said, I did go through my manuscript, that paper he wrote, about P conversions, and I found everything okay. So I believe that the problem is solved in this sense, that it justified your results theoretically. So the results that Zappo got, so from an engineer point of view, I think Babushka was the first who tried, or he succeeded to demonstrate the convergence or the P convergence of finite element analysis. So 81, I think that's where Babushka and Zappo has nothing to do with math, but he did published with Babushka a lot of papers, and that was the first paper in the 81 in Siam Journal of Numerical Analysis, where they proved the P conversions for finite element. 82, the software probe comes into life, and then the people, they use it. So Zappo also and Babushka published a book, which is Finite Element Analysis, also is very known. And later they started to do math. So I think this brief history just give you an overview what exactly happened to finite element, because when they start from 41 until 60s or 70s, so all that area was mainly dominated by engineering, from civil engineering, mechanical engineering. They do structures, fracture, they do also stresses, but no mathematician background or goes to that area. So we had to wait, I think, 20 years or more than 20 years to demonstrate that that method is converging, stable, and produce some nice results. So yeah, so once the mathematicians jump onto the board and they try to demonstrate these nice features, people, they get confident with those methods, and they start to work with. So, but I think the legacy, or the nice about any successful business has finite element is mainly due to computer power. So you cannot explain how finite element method is very well established without talking about computer power. So that driving force that take us or gives this legacy to finite element is computer and the power of the machines. So if you look at to what happened to the computers starting from 1930 up to 2020, so you see we had immense innovations and progress into from the computers and the power. So you start from, I think, 1930, where the first machine started, the one we call Turing machine, and then coming or along the years, you start to see very nice machines come to life, and with a high performance and very fast, very quick, and the less consumption for energy. And that's progress into machines. They give the power to finite element to be implemented to solve a very high complex systems. And also, if you look at something like what we call the law of Moore, so you see that the power of the machine increases very quick, very well, as it exponentially increase. We started with the CPU time machines that takes ages to run a simple code in the 60s. Now we can run the same code in fractions of seconds or minutes, and now we're starting to program with using GPUs and also quantum computers, and that's helped a lot the finite element to progress and to be well established. Yeah, if I show you just a simple comparison, if we see in the 30s, that's the machine people they used to run or to simulate stress analysis or doing some nice calculations. If you compare it to what we have up to now, so you see that's a machine which is the size of a house or maybe bigger, and this is the same machine, can be just a small handbag, and it does the same power or the same role. So if you look at on the 44, where the code maybe started to run that time, so that's the machine people they used. It's very huge, as I said, is a big machine and consumes a lot of energy, and to run a very simple finite element code with a few degrees of freedom. If you look at where we are now, this is the IP or the IBM high performance cluster, which is, I think, among the biggest or the fastest in the world. So, and you see the Chinese one, maybe this is the fastest supercomputer where people, they can do a lot of computation. So the reason why I'm showing this to tell you that finite element has profit or has benefits from this progress we had on the machines. And the people now, they do a lot of work on matter, as I said, seconds or minutes. However, there is challenges. All that progress we had in finite element methods, we still having problem when solving some kind of applications. And the problems that finite or the standard finite element method struggle is the fracture mechanics. So if you see here, so this is like a fracture, so this is a finite element mesh. You have the crack tip here, and then the stress starts to form, and then after a certain time, that will fail. So that's a simulation. Finite elements still struggle. This is not done by finite elements. You see the very high stress there, and then you have a failure or fracture, and that fracture is very hard to capture using finite element. So the same, so these are some applications where finite element, the standard one, I'm talking about finite element in a very conventional way. So if you see the fracture here, so again, you have to increase the size of the density of the mesh to capture those fractures. If you see, this is the impact, what is very known in the computational mechanics. So you have an impact of a ball into some fibers, and then you have the breaking of those fibers. This is the waves, could be any electromagnetic or just acoustics, and you see very small features which finite element which would struggle to get them. So this is why we need to improve finite element analysis. And the homework, or what I'm trying to show you today, is something very simple. So I usually, in my talk, I promise something, and if there is a promise to make into this presentation, this is what I want. This is how how can I explain it? Assume you have. Oops, sorry. So assume we have a harmonic, or just a wave, and this is a cylindrical wave. So you have this cylindrical wave with k is the wave number, which is very high, is 50 pi. And then I want to solve this in a different mesh and to try to see where the finite element can be very useful for this. So I solve this is a Helmholtz equation to make it very easy for people to understand. So, and then I take different meshes and I run the code and see what would get. So I will run the code into this mesh, which is a course which has 30 elements. And if I compute the solution, this is what I get on this mesh. And you see the error is very, very high. This is rubbish. It's not acceptable at all. Okay, so that's what we do on finite elements. So if this doesn't work, we go and refine the mesh and see what happens. So we refine the mesh into 3,200 elements and run the code, and that's what we get. We still get 65% of error. It's not acceptable. So we refine more and more. So this is a mesh which with 65,000 elements. And if I run the code on this, that sort of solution I get, which is still reasonable, but with a 5% error. Yeah, so that's what we get for different meshes. So the engineering, or what they ask, so can we produce this result, which is 0.1% of error, on a mesh with this? A mesh which is 8 elements only can give us a solution which is 0.1 error. So that's, I think, the dilemma and the homework we want to do. So today I show you, or I will show you, how can we use a sort of finite element on a very coarse mesh, which is 8 elements, and produce a solution which is 0.1%. And the miracle, or the key in this question to answer, is the enrichment. So can we enrich this mesh and get these results? Okay, as you see, on a mesh of 65,000, we are still far, which is 5%. So that's the question engineering they ask. Okay, good. So before I start my presentation, I need to acknowledge these people, because most of the work we have done is a collaboration with Heriot Watts and also some Nanjing University, and also some PhD students. I think Mustafa Malik, he already finished and he got a position in Pre-Milan University, is there. Mayank and Ganesh also have finished their PhDs, and now they got a postdoc. And Abdelwahid Wadri is the PhD now. He is fully working on this. So let me explain it to you very easy, and hopefully this would be very trivial. For those who work with finite element analysis, they know this. But if you haven't done any finite elements, don't worry, I will explain it well in few slides. So let us consider a very simple diffusion problem. So that's the variation of something. Q could be temperature, could be anything. And then you have a diffusion operator here, and then you have a source that releases either energy or temperature or heat or whatever. So that's diffusion coefficient. And then you have some Robin type boundary condition and some initial boundary or initial condition to have a well-posed problem. So we want to solve this problem using finite element. So we have a domain on space, a domain on time, we discretize this, and then we do the normal steps. So I use here alpha. It's nothing to do with the fractional derivative. So this is alpha just to tell you if alpha equal 1, we are in the heat equation or the diffusion problem. If alpha equal 2, then we have a wave problem, and then we can still use the finite or the enrichment for this wave or acoustics. So what are the type of problems we solved there in this project? So we mainly worked on heat transfer and radiative heat transfer. So if you do that, so that theta is the temperature, lambda is just a conduction or coefficient of diffusion, and then you have some absorption, scattering of radiation, and then phi is the radiative intensity. So you couple this to an elliptic type of PDEs where you have the intensity, radiation intensity, that's the thickness of the medium. Then you have a black body radiation that emit those photons or that generate the heat. Some emissivity on the boundary for the temperature, and also some boundary condition for the radiation, initial condition for the temperature. So that's a very known problem in radiative heat transfer, and that replaces the full radiative equation, because the full radiative equation is very complicated. It's integral differential equation, and then we do some asymptotic analysis, and then we reduce it to this SP1. We also did, so that's something Malik in his PhD he was dealing with. So we have a nonlinear terms here, so where the conduction depend on the temperature is a very known problem in the radiative heat transfer is Rosland. You still have the Planck function here, but we have a spectrum we have to discretize. These are the type of applications we are dealing with. And the last application I will show you a result on is the wave equation, where you have some potential or some acoustics here. C is the celerity of the wave, and then you have some source, and I will show you how can we enrich the finite element for these type of problems. You can reduce this second order partial differential equation into a first order by introducing the velocity, and then you will have a system of two equations. Okay, so what's the new about enriched finite element methods? So the procedure is almost the same. So if you have done finite element, the standard or the conventional one, so the starting point is the weak or the variational formulation. So we multiply by some test function or shape function or basis function, and then we discretize the weak function by inserting some discretized hat function, and then we assemble our matrices, the mass and stiffness matrix, and then we solve a linear system. So that's I think the steps for a finite element code. So weak form, discretization, assembly of mass and stiffness, and then linear system, solution of linear system. So that's exactly what we do. So if you remember the first equation, so what we do, we integrate, we multiply by some function, which we will call, the engineer, they call them hat functions or shape functions. We call them basis functions later. So then you integrate this operator here, you use the Gauss or the divergence theorem, and then you just take this integral into the boundaries. And that's what you get at the end. We use a Robin type boundary conditions. You get that integral over gamma, where the contribution from the boundary is coming from. Okay, so that's exactly what we call the weak form. Obviously, you need to choose the right spaces to be sure that the solution exists and is unique in some cases. And these spaces, though, the Sobolev spaces, depend on the type of boundary conditions you are dealing with, and also some regularities on the coefficient and the functions involved in your PDE. Okay, I'm not going to bother you too much about this, but this is a very well-known in people using finite element analysis. So then we have to discretize our spaces. So that's the space where we have to move from a continuous form to a discrete form, and there where we have to introduce the shape function to inject on that weak form. So that's something we do. So that's the discretized solution. So when we do the final standard finite element analysis, this will be just the sum over the model points. So the blue thing is the standard finite element. But when we do enrichment, or what we call babushka, they call partition of unity. And well, generalized finite element is the same. People on the fractal mechanics, they call it XFEM, extended finite element analysis. But all these words or this terminology or vocabulary means exactly the same. The only difference is how you enrich your basis functions. So if I cancel this black stuff here, I end up with the standard finite element analysis or discretization. However, when we do the enrichment, we introduce this another sum, and this is the sum run from the number of enrichments. That's Q, you see there is the number of enrichment functions we will add to our solution. And this is, again, this is the Galerkin projection here. So you see these G, which I call enrichment functions. That's where you have to put your unknown again. And this, you can show that this will verify the partition of unity, because you have a basis function, which is the standard one. Any multiplication of a function to that basis function will still be a basis for that space. Okay, so now we need to change something. We need to change the spaces, because we are introducing a new enrichment. And then this space, sorry, I need to go back. So this space here need to be changed, because that function or that solution we are looking for is no longer based on the usual Lagrange or basis function, but also should take into account these enrichment functions. Okay, so the question now, this is something engineering to be used. So this is why I want to, I use that title for my presentation, where mathematics can be useful here. So this is what the engineers do. So they embed this with some enrichment here, but they don't tell us how to choose these enrichment functions and how to choose these numbers, Q. Not like in the finite element, the standard one, where we know what kind of basis function we use, and the number would be dependent on what we call the P version of finite element. Okay, so these now we start to talk about Q version of finite element. So we need to choose these enrichment functions. So what has been used in the literature, so people, they use the fundamental solution. Well, this is mainly people working with boundary elements. They use the fundamental solution for the diffusion problem to also solve the problem. So that's exactly, if you take the enrichment functions, which are the fundamental solution, that would work, and then you can adjust these numbers here based on some calibration or some trial and error. What we use in our analysis, especially for diffusion problems, so we use the exponential. So that exponential involves the r, where the radius, which is the square root of x squared. And then we introduce some parameters to adjust based on your solution. So you have to get some intuition how your solution will behave, and that will give you the impression or the structure of these enriched functions. If you are dealing with boundary layers, so you need to think about some hyperbolic tangent, which can be used again as an enrichment function. To give you a rough idea, so that's the Gaussian. So if you have a diffusion problem, most of the time your solution behaves in this way. So you have something looks like exponential or Gaussian. So those are the type of enrichment functions you can only play on the number Q, and then you can inject as many as you want in your solution. If you are dealing with a boundary layer, this is a 1D case, just a cross section, but this is valid for 2, 3D. So if you're dealing with a boundary layer, so maybe the hyperbolic tangent would resolve that boundary layer, and then you can adjust these numbers based on the solution you expect. Okay, as I said, we need to change the space now. Instead of having the normal, so the blue stuff is the normal discretized solution, where you have just the model point and then the shape or the basis function. However, this time we have some enrichment, and this is why we add another degrees of freedom or another sum with those enriched function. I'm not going into the details, but if you know what finite element does, so you assemble these mass matrix, the stiffness matrix, and then you have the right-hand side. And if you take the first order partial differential equation, you end up, and then you use some time discretization, in this case Euler, so you end up with a system which looks like EX equal B, which is the standard for finite element analysis. However, the structure of these matrix and also the right-hand side will depend from the standard finite element to the enriched finite element. So for the enrichment now, we will have those entries for the matrix A, which are also sub-matrices. So each matrix here is a block of other matrices. So that's I think the extra thing compared to finite element in the standard way. So if you look at the entries of these matrices, you see there is a contribution coming from the enrichment function and also from the basis functions phi's. And that make these matrix dense, and it adds, of course, other degrees of freedom. A simple inspection of these matrices, so you see what I have plotted here. So that's the matrix A you get from the standard finite element on a structure mesh. You see you get a very nice structure, trade diagonal maybe, and then each dot you see here is one single value in your matrix. Now, if you take the same mesh and you do the partition of unity or the enrichment, so you end up with each dot here, it is a block of another matrix. So you get a dense, well, it's not, it's still sparse, a lot of zeros there, but any entry you get here is a small matrix, and the size of that matrix there is depend on the Q, the number of enrichment you put. If you do the same job, but this time using an unstructured mesh, so that's the structure you get. Remember, each dot you see here is one single value. If you do enrichment for the same mesh, that's the structure of the matrix you get. However, each entry here is still a small matrix. Okay. Let me show you some result before going into the other part, which deals with CFD. So all the results I will be showing you here is published on those papers starting from 2012, when we have done the first paper on diffusion problem. So then we applied the method also to the conduction radiation, and that's something we have used Gaussian enrichment. And later also we have done some heterogeneous media where we have a tensor in the diffusion term. We have also used the method for glass cooling, and then we have done some acoustic or electromagnetic waves. This paper, I think we were the first who published a paper on using iterative solver for these type of problems, because most of the engineering people, they do solve these using direct solvers. In this paper, we have done some iterative solvers. This one, we use it for inverse problem, and then we also did some nonlinear problems in 2014. Recently, we started to do 3D, so we have done 3D diffusion problems in 2019. I think we have done some also time domain wave using some explicit time discretization for the finite element. 3D problems in heat transfer, we have done it also. We done the Rosland problem, which is for the radiation also. Recently, this is the work by Abdouahid Woudri, who is doing a PhD. So we started to do Navier-Stokes equation using the enrichment as well. And that's where we do some uncertainty quantification. These two work published recently, I think. So anybody interested in this type of analysis or work, I'm happy to share these with you. Just drop me an email and then I send you those papers if you are interested. So the first thing I will show you is accuracy test. So accuracy test, we have an analytical solution of the problem, and then we want to quantify the errors. So we use two levels of meshes. So this is a coarse, we call it coarse mesh, and that's the fine mesh. So this is the for finite element, that's the standard one. And this is for the partition infinity, or just the enrichment function. So that's the mesh we want to run the simulation. And that's a finite element mesh. And we want to compare what's happened into the errors and also for the CPU time. So if you see the errors for different coarse and fine mesh, so you see the partition infinity is doing very well compared to the finite element and the coarse finite element. So you see that the errors are very far small compared to the finite element method, but these ones, they are using a very large meshes compared to the partition infinity. So if you take the fine mesh, again, you see the performance of the partition infinity is doing very well. And this epsilon you see there, this is for the asymptotic analysis, epsilon equal 1, that we don't have a boundary layer, but when epsilon equal small, you get a very sharp boundary layer. And for this case, you need more elements, especially for the standard finite element method. Now, well, we have to also talk about the drawback, not only the advantages of the method. So if I show you the distribution of the CPU time on different phases, so we are solving a couple problem, radiation and the heat. So you see the time consumed for each of these methods on building the system and solving it using a direct solver. So that building a system doesn't take too much, but solving it, that takes some time. And the bad thing, I think, here is the condition number. So if you compute the condition number, because the matrices you get from finite for the enriched finite element are very dense, so you see a very high condition number compared to the condition number you see for the standard finite element. So the standard finite element, the condition number is very small. However, if you look at the partition infinity or the enrichment, you see that the condition number is very high, and this is why people, they prefer to use direct solver, because most of the cases, the matrices are very ill conditioned, and you need to use the direct solvers instead of iterative solvers, unless you use some precondition. So if I show you what we have done also for the heat radiative transfer, so you see that boundary layer there, I'm zooming here. So I can capture similar results. This is for epsilon equal 1. This is epsilon 0, 1. You see very thin boundary layer there. So using a finite element mesh of this magnitude, I can use just this mesh, which is very, very coarse. I think this is 28 elements, and they can still capture the same feature, maybe better than the one on this finite element mesh. This is a 3D simulation again. So this is a engine part where we wanted to see the heat or the distribution of the temperature on this engine part. And again, this is the mesh we are using. So it's very coarse mesh, and it's very, very difficult to capture the features, especially on these small areas, without refining the mesh. But in our case, we were able to capture what's the temperature or the heat distribution into this part without any oscillations or any problems. So we also able to capture all these thermal boundary layers in the engine part. So we also did some acoustic waves. So this is the waves we solve. So you see we can use a very coarse mesh and then capture that the propagation for the wave here. So this is a scatter, and you see the waves, they just propagate. And this is a mesh of 8 elements. Okay, so let me try to cover in the remaining times what we have done for Navier-Stokes equation. I have the timer here. I'm conscious with time. I try to be quick to cover most of the stuff I'm planning to go through. So what we have done recently, this is starting from, I think, last 2 years, we're trying to apply the same for Navier-Stokes equation. If people working on CFD, they know what these equations model for. So you have the velocities, you have a pressure, you have a Reynolds number, and then we add some Coriolis term here, and then some friction on the bottom, and these are the wind friction terms. And we couple these Navier-Stokes equation for fluids to some concentration. This is a transport of a concentration C, could be any species. And then you have some diffusion term here and some source. And the idea was, can we enrich these or finite element solution for this problem? This problem is very tough, especially when the Reynolds number goes very high, and then this term or the convection becomes dominant, and most of the finite element method, they struggle. You need to stabilize them. So the idea, or this is the PhD thesis of Wahed al-Wadri, is to try to use a method of characteristics or the similar Lagrangian method to deal with this part, and at the same time enrich the finite element method. So what the method of characteristics does, so you integrate the equation along the characteristics, and then you use the fact that the solution is constant along the characteristics. So you split the domain or the problem into a convection part and then some Stokes or some diffusion part, and you try to solve them separately. So if you do that, so you compute the departure points for that flow particles with that velocity u, and for each mesh point, you compute those departure points, because a characteristic curves will start from this point to reach this point at time tn plus 1. And then you use the fact, as I said, that the solution at time n plus 1 is constant along the characteristics, will be nothing, just the solution at the previous time at that point there. Okay. So what we need here, so we need to search where the element that characteristic point belongs, and then use some interpolation to approximate the solution. So what we do, we use the Lagrange. So these are just the Lagrange basis function. We do the interpolation on the elements that K star is the element where the point or the characteristic departure point falls or belongs. So now, how to enrich? That's the crucial or the question we want to answer. If you do finite element analysis, so that's what this is a P1 linear. So for each of these nodal points, you look for the departure points, and then you interpolate using these P1 elements or basis function. If you do P2, this is a quadratic element. We have a 6 node, and you do the same. So for each of these nodes, you look for departure points, and then you interpolate, and that you get your solution for the convective part. Now, if you want to do the enrichment, that's the idea we come up with. So we can use some, we call them C0 because they are constant, piecewise constant function. And if you take the Lagrange basis function from P1 and P2 and multiply them by constant, they still do the job. So they still satisfy the partition of unity, of course. So the same what we have done here, this is just a location where we will put the degrees of freedom, and here we will use just a constant function to enrich these elements, for example, all these points here where we can put our degrees of freedom. Good. So the idea, as I said, is simple, like you do before. So this is just your solution is constant along the characteristics. That means the solution at time n plus 1 would be just the previous time, but calculated at this point. Now we need to do interpolation. So we don't do the standard finite element at this point. We do a projection. So we multiply by the basis function or the shape function. Those what you see here, we integrate. And then we take the advantage of finite element to assemble a matrix, which we call the mass matrix, of course, that will involve the integrals of phi I, phi g, and then we solve this system basis of element wise. So that's the system we have to solve. But this time, as you see here, so we have introduced those enrichment functions which are C0. So these are just the quadratic points to do the interpolation. Could be any constant here function, and then you have the number of degrees of freedom is this one multiplied by the number of elements. So we increase the number of degrees of freedom, but we don't change the mesh. The mesh remains constant. How can we solve this? This is a simple algorithm. So we generate the quadratic points onto each element. We assemble the mass matrix as usual. Then for each element in our mesh, we compute the departure point by solving this ordinary differential equation. Then we search and allocate where the characteristics belong. And then we compute our solution using the basis function at that point there by solving a linear system. We also, and this is what Abdul Wahid did in his PhD as well, so he tried to do adaptivity using enrichment where it is needed based on some criteria. So now, if you look at the algorithm, it's very simple. So for each time Tn, so what you do, you compute the criteria. So based on some estimation in each element, then you decide, do you enrich or not? If you enrich, that means you increase the quadratic points in that element, and then you do the standard way. So you construct the mass matrix, you solve the linear system, and then you check whether you have reached the time or not. If you decided not to enrich or to decrease the number of enrichments, so you do the same. So you still need to generate the point you want, and then you compute the departure points for that point. You compute the solution using quadratic interpolation, and then you solve the linear system. So that's an adaptive algorithm. So the criteria we use to do adaptivity for enrichment function is based for, this is for Navier-Stokes equation. If you do the convection diffusion, so it's, I think, easy to use just the gradient of the solution, but here we use the gradient of the velocity, and that gradient of velocity we also benefits from the characteristics, and that's computed at time n+1 because we go backwards in time. So if you compute that integral, will be just a small stiffness matrix here, and then that will be used as a criteria for adaptivity. Okay, I'll quickly show you some result. First of all, this is Burger's equation, which has analytical solution. So this is in 2D, so the difference only we don't have pressure here. Compared to Navier-Stokes, and then we will use a very high Reynolds number to try to neglect this term, and the convection will be the most dominant. Hopefully this would work. So if you see the different Reynolds number, different enrichment, and then we compute the L1, L2 error with some CPU time. So here we use a fixed enrichment, and this one we do adaptivity. So in terms of errors, you won't see a big difference. And however, if you look at the CPU time, so it is a big difference. So we can achieve the same error or similar error with a very small CPU time compared to the fixed one. The same for the V solution and the U solution. So why this doesn't work? So if, oh yeah. So if I show you what it does actually, so you have a shock, it's a very high Reynolds number, you have a shock propagating along the diagonal, and that the injection of enrichment function, as you see, is following where the shock is going, and that tells you the number of enrichment, each dot there tells you the number of enrichment function you are putting on each element. We are using a structured mesh, and that tells you where the enrichment is taking place. Oops. Okay, so if I do cross-section and show you the differences, so we have the exact solution for this problem. We have a solution on a very fixed refined enrichment, and we have the adaptive enrichment. So this is a Reynolds number which is 100, 1000, and 10,000. As long as you increase the Reynolds number, you see a shock which is very stiff shock there, as you see 1 point there. And as you see, so we capture almost the same solution for the fixed and adaptive. And here we'll see there is a difference, a discrepancy. We have an undershot and overshot there, which is usual for these type of problems. However, if we refine the mesh, you see a very nice coincidence between the fixed and adaptive solution compared to the analytical solution. We run this into the benchmark of flow around the cylinder, which shows us here. So this is the vorticity snapshots. You see the flow just when it hits the cylinder start to recirculate behind the cylinder. And these are the adaptivity or the enrichment functions along those high or low vorticity values. And you see that the mesh, we are not changing the mesh here. The mesh is fixed. All what is changing is the number of enrichment functions. So that means when we assemble the matrices, we don't need to change the basis function. The mesh is remain fixed. All what we do here is just inject the enrichment functions or decrease the number or increase the number based on some criteria for adaptivity. We compare the lift and the drag. This is the forces exerted on the cylinder. So we get something similar, force fixed and adaptive, but the CPU time used for the adaptive one is far more smaller than the one for fixed. I need to run because the time is almost done. So this is a problem which we use now for dispersion of a pollutant in the Mediterranean Sea. And again, as you see, so we have a release of a pollutant somewhere here, a concentration which you see here. So this is based on some input data we put on our Navier-Stokes equation or plus barometric model. And as you see, this plume or this concentration, once it started to propagate into the Mediterranean Sea, now the release stopped after 5 hours. And as you see, the adaptivity is doing the best work here. And you see those elements where we refined. Now there's no refinement, and everything or each element is going back to the normal. That means we don't have any injection for the enrichment function. So this means that the method is doing the right thing. So we also try to use this on the dispersion of phosphogypsum in the Gulf. This is a port in I think near Casablanca. So this is El Jadida. So this is a platform where I think the largest platform in the world processing phosphate, all that chemical release, or that they used and they threw it into the sea. This is a recent satellite image which shows how the phosphogypsum or the dispersion of that phosphogypsum is taking place. So that's something we are trying to simulate and apply this method to see whether we can capture this, and that can be helpful also for designing new pipe where to through them. So that's what Abdul Wahid is doing in his PhD as well. So you see that the plume, where we release here some concentration, and then using some conditions based on the data, and you see that the plume is doing something similar what the satellite captured, and here where the adaptivity or the enrichment taking place. Okay, so to resume, and that's my my second part in the title of my presentation. I think that's what the engineer is doing. So I am an applied mathematician, of course, that's what I learned, but I'm working in a school of engineering. I do a lot of business with engineering, but we are crying for mathematical proofs. Especially all what I show you, there is no analysis at all, so there is no conversions, nothing that can be based on these foundations that finite element method have. So what we are aiming to, so this is what really we want to do. So we develop some nice theorems. And the first thing we want to do is to develop a priori error estimates like the one we had, or Babushka did, and we have for the standard finite element. My question here, so there's no proof. This is why I said wanted, dead or alive. So can we prove something like this? So we have our solution, numerical one, and then we have the one for the system. Can we estimate an error that involves those enrichment functions? So for people working on analysis, this will involve enriching those nice Sobolev spaces to introduce the number of enrichment somewhere, and then based on some regularity onto the initial boundary conditions, can we estimate, or can we develop, or can we prove this theorem that the difference or the error between the two solutions is bounded by some constant which may depend on the solution and velocity. We're talking about convection diffusion here, and then you still have that estimate we might get for P version of finite element. And that would be a very good breakthrough on this area. So that's something we want to do. The second thing is, can we do a posteriori error estimate which also are very useful for this type of analysis or for this type of applications. And my idea or my dream, if you want, can we prove a theorem of this form? So we have our exact solution for the weak form, and can we have the estimators eta 1 to eta 6 somewhere? And these involve all the ingredients we have in our PDE, boundary conditions. Lambda is just a diffusion coefficient, and then you have the boundary condition with the type of Rubin. My colleagues in Heliot-Watt, they have implemented this and it works, but no proof. And where is the proof? I don't know. That's what it means in Arabic. So that's exactly what we want to talk about today. And as a summary, and I close here, yes, enriched finite element can do a very good job, can solve the partial differential equations in a very coarse mesh, and you get a very nice results. You don't need to change the mesh. You can solve many applications. People, they use it for fracture mechanics, they use it for acoustics, they use it for different applications. However, and especially for mathematical committee, so we don't have a theory. So these are still open questions. And this is where we need to work as mathematicians. And I'm very open to anybody who wants to collaborate on this area. And thank you very much.
Merci. Merci, thank you so much. C'est toujours très enrichissant de voir comme les mathématiques peuvent irriguer le monde des ingénieurs, mais là, vous nous avez montré quelque chose qui est un petit peu inverse, c'est-à-dire que ce sont finalement les ingénieurs qui sont venus apporter aux mathématiciens des idées nouvelles pour faire des mathématiques nouvelles, et maintenant les mathématiciens s'en sont emparés et manifestement ont encore du travail pour démontrer leurs idées ou celles qu'ils ont importées des ingénieurs. Est-ce que vous pouvez nous dire un petit mot sur les liens et sur la façon dont mathématiciens et utilisateurs de mathématiques se parlent? Par exemple, est-ce que les utilisateurs ont conscience de l'importance qu'il y aurait à disposer des démonstrations, ou est-ce que pour eux, dans la mesure où ça fonctionne, ils ne vont pas trop chercher plus loin?
Do you mean the interaction between mathematics and engineering, or if I understand very well?
Sorry, I can reformulate in English. I mean, sorry. I mean, you talked about the fact that first engineers developed new methods to solve their problems, and then mathematicians get involved. And but now mathematicians ask for proofs of the results or the methods, the validity of the methods, and then do the engineers are the engineers concerned by the necessity of proving things, or for them do they consider mostly that well, if things work, no need for proofs?
Yeah, that's a very good question here. So that's the discussion we have with engineering always. Yeah, so I think the difference between a mathematician and engineering is the mathematician wants to be right and the engineer wants to be correct. And there's a huge difference between right and correct. All the disaster we have is coming from engineering. So all these failures, the buildings, the dam that fails, or the bridge, or they are coming from engineering, because they do things, they try to be correct, not right. So they believe, if you talk to them, so they believe if the mathematician prove that this is based on some fundamentals, then they can use it with closed eyes. This is what they are doing now. They cannot use it with the closed eyes, because they believe, or they know 100% that something there is not really proved. So it converges, it gives the result, but that is not usual. So, and then they're looking for the conditions, because when mathematician, or we give them, look, you have a condition, and then they ask, is this condition necessary or sufficient? And that gives them a light. So the engineer, yes, they do brilliant job. They solve a lot of problems, but they do a lot of mess. If you look at what, so they try, but sometimes they fail. So if they have proofs, or they have confidence from mathematicians, they can do a lot of work, and this is exactly what's happened if you for finite element. So look, if you look at what I have presented at the beginning, so 41, the people Galerkin and also Clough, and they start to do analysis using finite element, but they didn't know what to do with it. So they said, well, we can solve the bridge, we can do a lot of work. But they wait until 60s and 70s where the mathematicians jump into the board and they show them, yes, that works. And that's why Babushka was very excited when he wrote to SWAPO, and they said, well, I proved those results are theoretically correct. And he was very happy, and he did a lot of business with him. Yes, so engineering, they need math, but they don't pronounce it loudly. I don't know why, but also some mathematicians, they don't pronounce loudly that they need engineering, but this is a different discussion, I think. But yeah, the question is very, very interesting.
So, thank you. On va passer maintenant aux questions du chat. So there is a question from Hamza Berga, who asked, in which kind of situation do we prefer to make use of finite elements instead of other methods? And he mentions volume or finite difference.
Wow, this is a very yeah, this I should have mentioned at the beginning. Yeah, so people who they don't believe in finite elements, maybe my talk was very boring for them. But yeah, you go to a doctor, and then he prescribe you some drug. So my talk is to those who already visited the doctor, and the doctor told them to use finite element. So if those who are not well, they don't have prescription for finite element, then yes, this is not the right way. Yes, I'm not really fanatic of anything, so I'm not like those people. They play football, they have their own team, they believe on the team, they can fight to the end. So I'm not going to fight for anything, but I don't believe in a key that opens all the doors. So that doesn't exist at all. Yes, there is problems where finite element can do very good job, but there is other problems. Finite element is a complete failure. It's not positive, it's not mass conservative, it's not. So for example, if you deal with the hyperbolic equations of conservation law, this would not be the best route to go. But yeah, so each PDE you are dealing with, it might find the key to open that PDE. Okay, yeah.
Okay, thank you. So another question is about link. So from Sukaina Wahab, links with differential geometry.
So sorry, link.
Is it linked in any way with differential geometry or part of it?
No. I think if you do fracture mechanics, then the mesh deforms, and like I showed in there, where that aspect should be injected into the enrichment function, and this is what people they do on XFEM, extended finite element. They start to enrich those cracked tip using some concept coming from the geometry of your domain, because like you see when you do fracture, so the domain starts to deform and you have a huge void starting to develop in the mesh, and that void should be incorporated in the enrichment function. Yeah, but for the domain, the one we use, no, there is no geometrical involvement there.
Okay, thank you. So another question by Hala Karkour, sorry for my pronunciation, about how can we illustrate the use of mathematics in cloud computing? I don't know if it's really linked to your talk, but possibly you have an idea on this.
Yeah, I think people now they start using cloud to do to run their code. Yeah, so you can buy an account from Amazon or from our cloud, and then you run your code there. Yes, that tools you can use for finite element as well. So, so people they use cloud computing as well to run the codes in parallel or in series.
And last question from the chat is from Adia Ashabak about how could PhD students study finite elements? Is there a best way, possibly a best book to start with?
I think finite element, well, depend whether now it is more known as a tool to solve PDEs. And people now, they stop doing work on finite element the standard way because they believe it's almost saturated domain. So people, they have already developed a nice theory. And now the finite element method is widely used as a tool to solve your PDEs. So you do your analysis, you prove anything you want. When you pass to the simulation, you can just run into finite element. It's a tool to validate your result rather than doing research in finite element. So, and there is many textbooks and courses online. So I think finite element methods, they are well established now. So
Professeur Benoît, il y a professeur Mrazli Zoubida qui a levé la main aussi.
Oui, on va donner la parole à ceux qui ont levé la main aussi. Allez-y.
Oui, professeur.
Ok. Merci beaucoup, Monsieur Seaid, pour cette belle conférence. Moi, je voudrais poser une question concernant la méthode entière, là, enrichie. Bon, elle semble plus performante que la méthode des éléments finis standard. Mais si j'ai bien compris, le prix à payer, c'est de perdre le caractère de creuse de la méthode, de la matrice, quand on va résoudre le système. Ma question est, est-ce qu'il y a une comparaison avec la méthode des éléments frontières qui n'utilise pas du tout de maillage et qui a aussi le désavantage d'avoir une matrice pleine, ou alors la méthode des éléments finis sans maillage? Est-ce qu'il y a une comparaison avec ces méthodes-là, puisque les trois perdent la qualité de matrice creuse qu'a la méthode des éléments finis?
Mais merci, professeur Mrazli. Si, il n'y a rien sans prix. Toujours, il y a un prix. Mais dépend how much we want to pay.
You can speak English.
Yes, that's easy for me. You make my life very easy. Yeah, so I agree. There is a price to pay in this type of methods. That the matrices are very dense, very bad condition, ill condition, and the condition number, for example, in acoustics, they can become 10 to 50, 55, which is huge. Yeah, but the advantage is using a very coarse mesh. That may be there is a balance between, do you want to use a coarse or fine mesh, and that's I think the partition of unity or the enrichment, they have this inconvenience. Yes, the people, they do cracks, and especially John Trevelyan, he did a lot of work in boundary elements, and they also enriched boundary elements. And the idea for cracks, they took it from boundary elements. So the crack tip, so they only discretize the boundary, and then they enrich the boundary elements, and they solve the problem. So there is a lot of works from engineering point of view, no theory, just to to clarify things. So these are people I know which are engineering. They did a lot of work enriching the meshless method using multi-quadric radial basis function. They enrich also boundary elements, but the inconvenience, like you said, is the matrices are very dense and air conditioned. And this is why another direction for research is to develop a preconditioner for this type of linear system. If we are able to develop a preconditioner, this will really answer a very good question. Yeah, this is why people need to do some work. Yeah.
Mais la comparaison entre les deux méthodes, est-ce qu'il y a une comparaison?
La comparaison, c'est toujours pour l'enrichissement. L'enrichissement donne la propriété d'utiliser un maillage très très grossier et tu l'enriches. Et l'avantage de plus, c'est que lorsqu'on fait l'adaptivité, on ne change pas le maillage reste constant. Et
non, ma question, excuse-moi, ma question c'est la comparaison avec la méthode des éléments frontières, par exemple.
Exactement, yes. Avec la méthode de boundary element ou la méthode de meshless, l'enrichissement est toujours favorable. Parce que boundary element, les matrices qui viennent de boundary element et de meshless elles ont la même propriété que la méthode d'enrichissement. Elles sont denses, mal conditionnées. Et si on fait une comparaison pour l'équation de Helmholtz, c'est ça ce qu'il a fait John Trevelyan, il a trouvé que la méthode d'enrichissement elle est plus avantageuse que la méthode des éléments de bande.
D'accord. Très bien. Merci.
Oui.
Alors, il y a aussi une question de Eloussel Quengel qui a levé la main.
Merci, Monsieur Benoît. Je remercie les organisateurs, professeur Alige et Benoît Rito, pour l'organisation de ce séminaire hebdomadaire. Aussi, M. Seaid, il organise ce séminaire en ligne pendant une année. Toujours, on assiste au couscous scientifique marocain le vendredi à 16h, depuis le confinement jusqu'à aujourd'hui. Je le félicite pour l'organisation et pour la qualité aussi des conférenciers, soit des professeurs, soit des étudiants en thèse. Monsieur Seaid, pour moi, c'est un exemple. Je ne peux pas l'attraper, impossible de l'attraper. Il a une énergie extraordinaire. Il aime la science. Il va être comme ça, il va continuer comme ça. Je l'ai connu en 2005. Lui, il est aussi très proche de moi parce qu'il appartient à la même ville natale, Azila, qui est une petite ville au bord de la mer, qui a connu une occupation portugaise. Et le roi Don Sébastien, lorsqu'elle est allée faire la guerre à Souaken, près de Ksarkbir, elle est partie d'Azila. Il est parti d'Azila avec la mentalité qu'il est gagnant à 100%. C'est une ville qui est, elle est très ancienne. il y a plus que 3600 ans. C'est là où il est vécu, Seaid. Donc, je l'ai connu, moi, en 2005. C'est la première conférence qui était animée à la faculté des sciences de Tétouan. En 2007, on a organisé 3 écoles de printemps, 2010, 2012, 2016, 2018 et 2020. On a essayé d'organiser la 4e ou la 5e école de printemps, mais malheureusement, on a le confinement et on a reporté ça. Et moi, je suis théoricien de nature. Je fais ma thèse en France, je suis revenu. À un certain moment, j'ai rencontré un écrivain, il est d'Azila, mais il avait un poste au cabinet royal. Il m'a dit, qu'est-ce que tu as fait? Qu'est-ce que tu fais? Je lui ai dit que je fais des mathématiques appliquées. À l'époque, je ne connais pas ce que ça veut dire les mathématiques appliquées. Donc, je connais les mathématiques appliquées à travers M. Seaid. Donc, pour moi, un grand merci. Maintenant, je vais entrer dans le sujet. Donc, quel est le lien entre les mathématiques et l'ingénierie? Il y a une complémentarité entre les deux. On ne peut pas être un ingénieur sans de faire ce genre de choses sans les mathématiques. Ce sont deux choses complémentaires pour moi. Aujourd'hui, on a écouté plusieurs choses. On a écouté la modélisation, on a écouté l'analyse fonctionnelle appliquée, on a écouté l'informatique, la résolution de systèmes linéaires, le côté physique, on a écouté la partition d'unité qui est qu'on l'utilise dans la distribution, l'analyse fonctionnelle appliquée. Donc, on a écouté plein de choses de mathématiques. Mais ce qui est important ici, c'est qu'on donne beaucoup de valeur aux mathématiques. Les mathématiciens, moi, chaque fois que je discute avec Seaid un problème, il me dit, est-ce qu'il y a un cas réel? Est-ce qu'il y a un cas réel là-dessus? Donc, pour pouvoir servir les gens. Maintenant, je vais entrer dans le sujet, je vais donner des questions à Seaid. Donc, les éléments finis enrichis, bien évidemment, on gagne dans la précision de la méthode, mais on perd quelque chose. Donc, cette perte, elle est démontrée dans les perspectives, c'est-à-dire réduire de travail sur le conditionnement de la matrice. C'est-à-dire, on a un système linéaire beaucoup plus complexe qu'il faut résoudre. Donc là, les algébristes peuvent investir là-dessus et de travailler dans le conditionnement des matrices de grande taille. Et ça fait un très bon sujet de recherche là-dessus. Donc, pour moi, lorsque je ne travaille pas sur les éléments finis enrichis, mais j'ai analysé son exposé, donc il utilise les gaussiennes. Pour moi, est-ce qu'il y a d'autres fonctions autres que les gaussiennes qu'on peut tester dans les éléments finis enrichis? Est-ce qu'on peut tester les polynômes orthogonaux qui ont des propriétés très importantes pour les éléments finis enrichis, et puisqu'on a un code de calcul, donc juste changer là où il faut changer pour tester ces gens-là, ces trucs. Une autre question, c'est que est-ce qu'on peut utiliser les éléments finis enrichis dans les problèmes à frontières libres? Ça, d'un côté. D'autre côté, est-ce que vous avez testé ou bien vous avez essayé de tester les éléments finis enrichis pour des domaines qui ont des bords non réguliers? C'est très important, ce genre de sujet. Et le dernier mot, est-ce que vous pouvez nous dire le temps de calcul pour pouvoir tourner différents problèmes qu'on a écoutés aujourd'hui? Et merci tout le monde.
Merci, Naji. C'est un plaisir d'avoir avec nous. pour la dernière question, le temps de calcul dépend de la machine, bien sûr, mais en comparaison avec les éléments finis standards, l'avantage, c'est d'utiliser un maillage grossier. Si vous utilisez le même maillage que les éléments finis enrichis, bien sûr, les éléments enrichis sont très longs, parce que le nombre de degrés de liberté sont très grands en comparaison avec les éléments finis standards. Mais l'avantage, c'est d'utiliser un maillage très, très grossier et de développer des fonctions d'enrichissement qui donnent un nombre de degrés of freedom ressemblable à les éléments finis standards. Mais toujours, les éléments finis enrichis ne sont pas très longs en comparant avec les éléments finis standards. Pour la première question, c'est le choix des éléments, des fonctions d'enrichissement. Ça, c'est une question ouverte. Parce que, comme j'ai dit, il n'y a pas une théorie. C'est des techniciens, ce sont des ingénieurs qui essayent plusieurs choix et à la fin, ils arrivent à prendre une fonction qui donne ce qu'ils veulent. Je connais des gens aux États-Unis, c'est le Milan qui est doing. Ce qu'ils font, ils sauvent le problème sur un maillage grossier, d'avoir une impression sur la solution, comment se comporte. Et ça, ce comportement nous donne l'information comment développer les fonctions d'enrichissement. Ça, c'est une procédure, c'est pré-processé, on sauve le problème sur un maillage et on voit comment la solution comporte et on essaie de construire les fonctions d'enrichissement qui ont les mêmes comportements. Il y a des gens aussi, ce sont des ingénieurs qui font l'enrichissement local. Ce n'est pas l'enrichissement global comme on fait ici, parce que les fonctions d'enrichissement qu'on a, c'est des fonctions qui sont globales, c'est tout le domaine. Mais il y a des ingénieurs qui font, surtout les gens qui font l'ingénierie de fracture et des structures, ils font des enrichissements locaux à partir d'un élément. Il y a même il y a des enrichissements discrets, c'est pas continu. C'est juste des solutions locaux. Il y a un travail de Shabbat ou Farhat, il fait d'enrichissement de digi, de discontinuous hierarchy. Et ça, c'est local, toujours. Pour la question sur la frontière libre, bien sûr, il y a des gens qui font la déformation ou les problèmes d'ingénierie, il y a une frontière libre. Il y a le problème surtout la déformation, élasticité, plasticité, tout ça, c'est des frontières qui bougent avec la solution, et même les domaines n'ont pas, le bord n'est pas régulier, Ok.
Bien, merci beaucoup. On va devoir arrêter là. Je pense qu'on a un petit peu débordé. Donc,
C'est professeur,
très vite alors.
professeur Benoît, monsieur Hussein Kanjel a levé la main il y a longtemps.
Ah oui, pardon, je croyais que c'était à vous de donner la. Oui, alors, allez-y rapidement et puis on arrêtera après.
Ça marche. Merci, c'est Mohammed pour ton exposé. J'avais quelques questions, mais une a été posée par M. Nagy, l'autre, je pense que vous venez de répondre. Ça dépend si c'était une méthode globale ou locale. Donc, comme vous avez dit, c'était global. Je me demande si, comme tu enriches sur un maillage grossier ou par élément, est-ce qu'il n'y a pas un moyen d'éliminer les degrés de liberté que tu rajoutes dans le triangle, par exemple, avant de résoudre le système complet? Ça, c'est la première question. La deuxième, c'est le préconditionneur. est-ce que vous avez essayé les préconditionneurs qui existent déjà dans la littérature? Est-ce qu'elles marchent ou pas? Et c'est pour cela qu'il y a des problèmes ouverts dans ce sens. Et merci.
Merci. C'est des bonnes questions. Peut-être le micro. Ok, perfect. Pour le global et le local, c'est ça ce qu'on fait pour l'adaptation. On ne garde pas le même degré de freedom pour l'élément. À chaque fois, on raffine, on déraffine. Ça veut dire si le critère d'adaptation nous dit que cet élément doit être enrichi et l'autre, le critère n'est pas satisfait, on dérachine, on dit, je ne sais pas si le mot est correct ou non, mais c'est raffinement et déraffinement. C'est la même chose qu'on fait avec l'adaptation de maillage, mais ici, on fait l'adaptation sur les fonctions d'enrichissement. Il y a des éléments qu'on va enrichir et d'autres éléments qui ont été enrichis, on doit enlever ce enrichissement. Il y a raffinement et déraffinement, mais ce n'est pas un changement de maillage. Le maillage reste toujours le même, la connectivité et la distribution des nodes, des éléments, et tout ça, c'est le même. On ajoute seulement des fonctions d'enrichissement ou élever les autres. Pour les préconditionnements, c'est un très bon area de recherche et j'ai commencé, on a déjà publié un papier pour les méthodes itératives, mais sans préconditionnement, avec des gens de littoral, l'université littorale de Calais, mais les gens, surtout côté engineering, ils ont investi beaucoup sur les solvers, direct solvers, surtout SVD, toutes les méthodes qui sont bien établies. Il y a toute une théorie, tout un mécanisme, il y a beaucoup. Et pour nous, les matheux surtout, pour convaincre un ingénieur d'utiliser ce type de méthode, c'est très, très difficile. Ils ont utilisé ces méthodes pour toute la vie et ça marche et donne des résultats. Mais pour nous, développer des préconditionnels pour solver ce type de système, c'est un domaine qui est très, très, très intéressant. Et si on arrive à développer des méthodes de multimaillage, par exemple, ou d'autres préconditionnels, ça sera très bien parce que, at least, on va diminuer le coût à la moitié. Et si quelqu'un est intéressé à ce sujet, nous sommes ouverts tout.
Bien, merci beaucoup. Merci encore pour cette présentation et pour cette séance de questions tout à fait riche. Je passe la parole à Arige, qui va nous dire un petit mot pour la prochaine séance. Et bonsoir à tous.
Merci.
Merci Benoît. Avant de clôturer, alors je veux demander à mon collègue professeur Farrahi, est-ce qu'il y a des questions via Facebook? Professeur Farrahi, un dernier mot avant de clôturer. Veuillez activer votre micro.
Oui. Merci. Non, pour le moment, nous avons d'autres questions davantage. Bon, je pense que nous avons fait le tour. Il y avait donc peut-être une dernière, mais je n'arrive pas à la retrouver sur le chat de Google Meet. Mais sinon, je pense que le professeur Seaid a fait le tour, le professeur Rito donc a présenté l'ensemble des questions. Donc, je pense que c'est bon, nous pouvons donc clôturer cette séance aujourd'hui. Merci, professeur Bouguel.
Merci, professeur Farrahi. Alors, merci aussi, professeur Benoît. Donc, merci, professeur Seaid, pour cette conférence très, très riche qui donne et qui montre l'importance des éléments finis enrichis pour la résolution numérique des équations aux dérivées partielles et bien sûr pour la performance et la précision des solutions. Alors, avant bien sûr, de mentionner la prochaine conférence, professeur Seaid, un dernier mot aux participants.
Merci beaucoup, c'est un honneur pour moi. C'est toujours un plaisir de voir des amis, des collègues, et des étudiants, des futurs enseignants. Merci tous, merci Bouchaïd, merci Benoît, merci Arij, c'est un grand plaisir pour nous. Merci.
Oui, merci remerciements. Alors aussi à tous les professeurs, à tous les doctorants d'avoir participé aux discussions en mathématiques franco-marocaines. Alors je vous donne rendez-vous la semaine prochaine, le mercredi 14 avril, avec le professeur Mohammed à 16h, bien sûr GMT plus 1 heure, sous le thème utilité dynamique progressive. Alors, je vous souhaite Ramadan Karim, Ramadan Mubarak, Inch'Allah, alors avec une autre conférence des discussions mathématiques franco-marocaines. Au revoir à tous. Merci beaucoup.
Merci. Au revoir.